Hi, everyone. Welcome to our third and final lecture for Unit 7. In this lecture, we're going to take what we've learned about volcanism on the Earth and we're going to apply it to the various locations where volcanism is happening in our solar system. So, finishing up this unit, you will need to describe how we think lava tubes have formed on the surface of Mercury. We will then turn our attention to Venus and its numerous volcanic features, and even talk about how Venus is possibly still volcanically active today. Then we'll talk about how the moon has large areas of lava that have formed into rock known as the Maria. And then we will talk about volcanic regions on the surface of Mars, particularly the region known as Tharsis. And then finally, we'll talk about volcanism on moons in the outer solar system, in particularly Jupiter's moon Io. So here is a family portrait of our inner solar system, and we will make our way through the various planets in our moon. So starting with Mercury, we've known Mercury really for its strange crust as well as its large impact craters. However, there is evidence that volcanism occurred early in Mercury's history. When we see Mercury's surface, we see large areas that are very rough, such as up here in the corner. They have a very high and irregular mountainous texture that is very covered in a lot of craters. But then we see areas that appeared to have one time possibly been very smooth and covered by fewer craters. And so ultimately, these areas seem to have been pre-existing lows or basins or valleys that were then filled in by volcanic lava. And then over time, that surface was then impacted by smaller craters over time. The larger craters hit these older surfaces, but then smaller craters hit these younger surfaces. And then with the volume and space area that we talked about with Mercury, this surface was then tectonically deformed by those compressive stresses. So we see those faults, those reverse faults, those thrusts and scarps forming on Mercury's surface. Interestingly, Mercury has what are possibly exposed lava tubes. Here we see on this image, remember, with these impact craters, we can tell which way the sunlight is coming from by looking at the shadows. We know that this is a low area. There's a low area in here, and there's a low area in these craters as well. And that sunlight is coming in from the left side of the page because it is casting a shadow on the left side of these craters. When we look at the center of the image, we begin to see that there is a valley that is cutting its way through Mercury's landscape. We see that there's a shadow on the left side, and it is very bright where the sunlight is hitting the valley wall on the right side. So we're able to see that there is a canyon or valley making its way through this part of Mercury. See another example here that we see the sunlight coming in this time from the opposite direction. Sunlight is coming in from maybe the top of the image or from the right side of the image, and it is shining and reflecting off of the lower right side of these craters. Simultaneously, there is a shadow on the north and right side of these craters. I think I got the left side mixed up. However, with that, we can then see that there's a valley that sort of connects this crater up here into the north. How could these valleys form? Well, on Earth, we usually associate valleys with water and erosion. However, there's no indication that there could really be any water ever active on the surface of Mercury. We're much too close to the sun, and there's really no atmosphere to preserve any sort of hydrological cycle. So the one hypothesis that remains is that these are lava tubes. Lava tubes form on Earth when lava is flowing over the surface, and after a given time, that lava begins to melt its way into the underlying part of the landscape. Simultaneously, the part of the lava that is being exposed to the surface is cooling down really quickly. Everything inside the lava channel is remaining nice and hot, but the part of the lava that is closest to the atmosphere is going to begin to cool more quickly. And so over time, the lava tube will begin to form as the top part of the lava begins to seal up and the lava inside the tube begins to continue to melt its way down. Ultimately, what ends up happening is after the volcano in that area has become extinct, that lava tube is remained inside the ground and lava has sort of covered it up, or sediments have covered it up. Eventually, that area will become unstable and those lava tubes will be exposed to the surface as the roofs of those lava tubes collapse. I got the experience of being able to hike through one of these lava tubes in New Mexico as a college student. And as you can see, that the roof of this lava tube is basically fallen down and collapsed. And it also makes a great place to sort of begin your hike and start exploring the lava tube. This is actually really dangerous. This is a super steep climb. None of us had special gear, but it was really fun and really cool to get deep inside of this lava tube. And so we can see how these valleys or these canyons could have possibly at one time been lava tubes that have then collapsed and now are exposing the insides of those lava tubes out for us to see with our images. Next up, we have Venus. Venus is super hot due to that very thick atmosphere that it is covered by. We want to remind ourselves that there are a couple reasons why we do not see very many craters on the surface of Venus. The absence of craters is one, we already know, is due to that thick atmosphere. It prevents smaller objects from ever reaching the surface. They burn up due to the high amounts of friction and heat that are created as they make their way down. The other thing that we haven't emphasized is the amount of volcanism that has been occurring on the surface of Venus over time. That volcanism, just like with erosion, is capable of removing that crater from the surface. It's able to cover it up and fill it in. And so what kinds of volcanoes do we have on Venus? Well, we have a number of different kinds. We think we have many, many large shield volcanoes on the surface of Venus. We think that we've identified about 167 volcanoes that are larger than 100 kilometers. Remember, the shield volcanoes on Earth are nowhere near in the size, so we have very, very large shield volcanoes, and we have a lot of them on Venus. They tend to be much larger, probably because of the high surface temperatures that are present on Venus. This allows that lava to stay molten for a longer distance, and so that lava is able to move out wider to a wider area and create a larger volcano. There are also these really weird features called pancake domes. They're about 1 to 5 kilometers in diameter, and they are thought to form when magma makes its way near to the surface and begins to bulge, cause the surface to bulge outwards. And so ultimately it ends up forming somewhat of a dome that then ultimately that lava or that magma retreats back deep into Venus's crust. And ultimately that lava dome kind of collapses in on itself and cracks, leaving sort of these pancake dome-like features present on the Martian surface. We're still not entirely sure how these form, but we think that this is sort of the dynamic that is at play here. The next feature are coronae. These are thought to be gigantic lava domes, similar to the pancake domes that we were just looking at. Instead of forming pancakes or domes, they form these massive circular rings that are basically radiating fractures throughout the Venusian crust. These things can be hundreds or thousands of kilometers in diameter. And so these are massive places where magma is at work deep within the crust of Venus, and it is bulging up to the surface, forming cracks that end up radiating in a pattern that are in a circle. So this begs the question, does Venus have volcanoes active on its surface today? We see lots of evidence of volcanism in its past, but are any volcanoes currently active? Well, we have some evidence that suggests that there are volcanoes that are active on the surface of Venus. The first come from volcanic gas emissions, different satellites that we have sent to Venus and different telescopes that we have pointed towards Venus suggest changes in the amount of sulfur that is present in Venus's atmosphere. These changes in sulfur could be directly related to the gases that are emitted from the volcanoes. The second is the detection of possible volcanic lightning. Here is an image from a volcano in South America that as this volcano was erupting, the particles that were being released into the atmosphere caused a static charge to build up in the atmosphere that was then discharged in the form of lightning. So this volcanic lightning has been documented in many cases for volcanoes on Earth. And it's thought that some of our spacecraft that took along with them radio antenna were able to pick up the sounds of these kinds of lightning strikes that were happening on the surface of Venus, that perhaps some of that material was being thrown into Venus's atmosphere and it was causing lightning strikes just as we see on Earth. And then finally, we've seen surface temperatures dramatically change on the surface of Venus. We have a thermal image of this area here, and then on the next time the satellite took an image of this area of Venus, it was able to detect changes in the surface temperature for discrete areas, indicating this could be a new place where lava was just deposited onto the surface of Venus by a new volcano. So ultimately, we see many different lines of evidence that suggest that volcanoes are still active on the surface of Venus today. Then this takes us to the moon. The moon has these two types of crusts. We have the large or lightish southern highlands, which have a lot of craters on them. And then we have the mare, which are these dark circular patches that tend to have fewer craters than the cratered highlands. How did the mare form? Well, it is thought that they are the result of both very, very large impacts into the southern highland crust that was formed initially. And these large impacts were so deep into the surface of the moon that they actually broke holes into the lunar mantle. This mantle would then erupt out and fill these large impact basins with the lava that was generated directly from the mantle. And so ultimately, coming from the mantle, this stuff has very rich in iron and magnesium. And so ultimately, we end up getting a different color because of the different composition that the lunar's mantle contained relative to the lunar crust. So ultimately, here's a diagram. It shows the lunar magma ocean. As the moon is differentiating, we can see that we have different layers of the moon that are separated by their composition and by density. However, these massive impacts basically broke holes into the deeper and dense layers deep within the moon. And then that material was able to come up and fill in those ancient impact basins. Finally, we have Mars. Mars is our last planet in the inner solar system, and it is also covered by very, very large volcanoes. Tharsis is the region that is best known for the largest volcanoes in the solar system. Olympus Mons is the largest mountain and the largest volcano in the solar system. It is about 25 kilometers tall, which is about 4 times the size of Mount Everest. And this volcano rises above even Mars's very thin atmosphere. Just to give you an idea of the overall size, Olympus Mons is about the same size as the state of Arizona. Olympus Mons and all of these very large volcanoes are all shield volcanoes, basically indicating that Mars has a very low viscosity lava that is mafic in composition. And so ultimately, even though these volcanoes are very tall, they are also very wide, similar to the shield volcanoes that we see on Earth. Then the question becomes, is Mars still volcanically active? This is a tougher question to ask than the one for Venus. We have no direct evidence that there are ongoing eruptions on Mars. So that is a little bit of a tricky question to then answer. Some of our counting and age dating for the Martian surface suggests that the youngest lava flows may be about 10 million years old, which isn't very young, but in terms of how old Mars is, that is relatively geologically recent. The InSight lander was sent to Mars to kind of help ask this question by trying to get an idea of how is heat transferred from the interior of Mars to the exterior. And they ultimately tried to also detect Martian earthquakes. And they have been able to detect Martian earthquakes, but they're having a difficult time getting an idea how hot things are deeper within the Earth, because their drill ended up failing and was not able to go very deep. It was actually very tragic. It got stuck like less than a foot down. Finally, we'll make our stop in the outer solar system to Jupiter's moon Io. Io is a beautiful yellow sulfur moon. It is Jupiter's innermost moon, and because of that, it is susceptible to very strong tidal gravitational forces. These forces are due to what are called orbital resonances. These orbital resonances are basically synchronized or patterns in the way that the moons orbit around Jupiter. So in this orbital resonance, you will see that every time that Ganymede goes around Jupiter once, Io has effectively gone around Jupiter 4 times. Every time Europa has gone around Jupiter once, Io has gone around Jupiter twice. Ultimately, what this means is that Jupiter and its moons will be on opposite sides of Io at multiple times throughout its orbit. What this essentially does, though, is it causes Io to be stuck in a tug of war between Jupiter and its other moons. When Io goes by Europa, Jupiter is always pulling on it, but once Io gets close to Europa, like right here, or when it gets close to Ganymede, like right there, or right there, and then when Io gets close to Jupiter and Ganymede at a similar time, those moons are going to pull on Io in the opposite direction that Jupiter is pulling on Io. And so the interior of Io is essentially doing this. It's flexing because it's getting pulled by the moons and Jupiter in opposite direction. And if you've ever taken a paper clip and bent it back and forth, you'll know that that flexing generates heat. And so Io is generating heat due to these gravitational pulls from its interior. And ultimately, what that results in is a surface that is completely covered by volcanoes that are very active on its surface. We're out in the outer solar system, so the material changes. There's a lot more water, there's sulfur, there's sodium, and so we're getting a change in the color and the composition. But these are still volcanoes. We see that they tend to form more of a caldera-like shape. Here we see a caldera depression. We see maybe a volcanic edifice building up, maybe another volcano and a lava flow occurring down here, as well as here. But what is probably most spectacular about Io are the volcanic plumes that are erupting from the surface and sending volcanic pyroclastic material, Io's composition, related to Io's composition, out into the solar system, and then that material is then raining down on top of Io. So Io is, in fact, the most geologically active. It is constantly in eruption. There are actually multiple volcanoes that are erupting constantly on Io at any given time. We can see this large volcanic eruption, Pele, here. You can see another volcano erupting just off the corner here. And then if you look closely, you can see the sunlight reflecting off of the atmosphere, or not the atmosphere, the particles here on this side. So we see multiple eruptions occurring on Io, and it is directly due to its patterns of rotation. So I wanted to end on an exciting note, the most volcanically active body in our solar system. This has been Unit 7. I will see you all later this week in Unit 8. Hope you have a great rest of your day.